Welcome students for the lecture 17, that is crop modeling concepts and compartment model symbols. So, earlier we have discussed about the basics of the crop modeling, say terminology, introductions and understanding about the crop model. Today we will discussing about these concepts and also give the compartment model symbols, because these symbols are used for you can say for the describing the representing the models in the logic and the flow charts, that helps understanding of the input output relationship, flow in the models and the simulation process. So, for this lecture, so let us have this. So, what the crop model concepts? If you see the crop models that discussed is simulate the biological, physical and chemical processes that governing to crop growth and yield. This is a biophysical model, is a mechanistic model, where this is based upon some of the preconceived biological theory and the understanding. So, that simulate the biological process, physical process and the chemical processes that leads to crop growth and yield. So, they integrate the genetic potential, genetic characteristic of the crop with the environments and management practices. So, that to have the predict the crop performance. The model describe the processes which are in the crop models. You can see these are the you can say this is a photosynthesis. Just a moment. These processes like the photosynthesis and the respiration. So, that is as a module simulated in the crop model. Then the biomass accumulations and partitioning, because the biomass accumulated in the crop, that is partitioned to different organs like leaf, stem, root and the flower and the fruits, and the water and nutrient uptake also, that is simulated in the model. So, water uptake and the nutrient uptake in the crop model. Phenological development stages. So, we have discussed earlier. So, what are the phenological developments? So, like for rice example, like tillering, then comes panicle initiation, flowering, grain filling and maturity. So, these are the progress of the developmental stages. So, these are the model describe the processes. The processes are as a different modules. They are simulated in the crop models, photosynthesis, respirations, biomass accumulation, biomass partitioning, different plant parts, water and nutrient uptake by the plants and the phenological development. Then this is used to evaluate the effect of climate, effect of the soil and the managements on yield and sustainability. This we apply the crop models like yield forecasting for the few years, or the long range yield forecasting for the 10 years, 20 years, then crop systems optimization. So, different the plant systems, nutrient uptakes, water uptakes, climate impact assessments. So, how do you understand the effect of the climate change? It may be rising carbon dioxide, rising temperature, change in radiations. So, how they are going to influence the ultimately the crop biomass and the crop yield. Then resource use efficiency analysis, how we can optimize resources applications, particularly water, nutrients and of course, the plant protection measures, pesticides, because now the pesticide use of the intensive use of pesticides, chemical pesticide, that causes lot of the health issues. So, using crop models we can optimize how much the amount of pesticides should be used for the maximum productions without affecting the human health. So, with this is the concept of crop models as we are discussing. Then I can see this the system representation crop modeling. So, what it does, a system is a set of interrelated components that operate together towards a goal. So, the system that crop modeling that encompasses that use the inputs, particularly use the weather, the soil inputs, water, nutrients, managements, the environmental inputs and the management inputs, that gives together as a input for the crop models. We will be discussing particularly example of a software DSAT. After we finish the crop modeling concepts and the crop model simulations, we will go to hands on experience of a model software DSAT, decision support system for agrotechnical transfer. So, there we will be discussing the input data entry. So, how the data to be entered in the DSAT format like weather data and then your soil data, then your management data, crop management data. Then in the processes you have the, as you discussed earlier, the processes, there is a crop physiological biophysical processes, the uptake of the water and nutrients, then the photosynthesis, respirations, these are the nutrient uptake, these are processes are the simulated in the model. Finally, you get the outputs like yield, biomass, water use, nutrient balance, these outputs you get. So, these are the input data entry, then processes that is simulated in the model, and the outputs we get the yield, we can get the biomass, we can get the water use, or we can get the nutrient balance, carbon sequestration, greenhouse gas emission. As per the user's interest, we can get the output through using this model. Then also relationship among the inputs and outputs are expressed in the mathematical equations in this model. What is the input output system? The core the objectives of the crop modeling, you can say model is developed, how the input output cause and effect relation that is established in this model. Then systems are dynamic, outputs vary with time and management practices definitely. Then crop system model thus represent the real world ecosystem in simplified and computable form. So, this is the representation of the crop model. So, you give the input parameters, input data, input the environmental inputs and the soil inputs and the management inputs, these are the major inputs for the crop modeling. Then they have the processes, biophysical processes in the crop model. So, that photosynthesis, respirations, nutrient uptake, water uptake, and finally, the biomass partitioning and the yield simulation. Those processes that is inside the crop models, and based upon that processes we get the final output as per the user interest, either the yield, biomass, water use, nutrient balance, carbon sequestration or greenhouse gas emission. So, these are the system. So, what is the crop model? We use in the compartment model symbols. What is the compartment model? Because now this compartment modeling concept is used for the application in other fields. So, this here also now used in agricultural field, particularly the symbols of compartment models that helps for to represent the crop model's input output relationship, how the flow occurs within that model. So, that was the crop models use compartment models to represent different components of the agro ecosystems, and that simplifies the relationship between the inputs, how the flow occurs between the variables also, that can be represented by this compartment models. A compartment is a homogeneous unit that is containing a measurable quantity. So, that is either the state variable, you can say compartment that indicates a state variables. So, it represents as a state of the systems at any point of time. So, the quantities, this is quantified as a soil nitrogen content, crop biomass, soil water, leaf weight, stem weight. So, these are the state variables that are represented by compartment. So, we will discuss about the different symbols of this compartment models. Then flows between compartment represents exchange or the transformations, that is the nutrient uptake or the drainage of the water, biomass partitioning, flow of biomass. So, that can be represented using this compartment model symbols. So, this is a usually the that is a rate change of each compartment, it is given by the input output relationship, inflow and outflow. So, dx I by dt, this is a state variable you can say. So, the rate of the changes of state variables per unit time. So, if you differentiate dx by dt is the inflow rate minus outflow rate. So, this principle is used for crop modeling simulation. So, change of the you can say biomass per unit time, that say or the carbohydrate accumulation particularly per unit time. So, this inflow is say the say gross photosynthesis and outflow is the respiration. So, net photosynthetic accumulation, that is a dx I by dt, and that gets conversions to the biomass. So, this we will discuss what the inflow and outflow relationship, the inflow rates and the outflow rates, that gives the change of the particular state variables per unit time. So, that is what the rate change, this is explained in the compartment model. The compartment model follow the law of mass conservation, that is nothing is lost or created arbitrarily. So, let us say input and output. So, inflow and outflow. So, rate of inflow minus the rate of outflow, that gives change in that components per unit time. So, these models are the core to the crop, soil and hydrological simulations. This is we will be discussing about what are the symbols, those are used in this compartment model to signify, to represent. So, each of the different components in the model. So, these are the Forester is scientist. So, notation 1961. So, these symbols introduced by these symbols by J. W. Forester to visualize the systems in a dynamic modeling. How we can see the operations of a system, operation of a model. We can also understand the input output relationship, how the different inputs, different variables, they do interact with each other by using these symbols. If you see the flow chart of the symbol of a model, from there that can give a better visualizations or the understanding about the cause and effect relationship in the model. So, those are represented by the symbol. This is very important one. You should understand the when you write the models and make a flow chart. So, this is essential to understand the different symbols. So, that you will be able to make a flow chart for a different processes in the model. Suppose you can say the photosynthesis or the partitioning of the biomass or the water uptake and nutrient uptake, how they are simulated in this crop model. So, used widely in agricultural and environmental modeling, these symbols are applied, provides a visual representation of interactions, feedback loops and dependencies. So, what I saying, if you see the flow chart of any process in a model, you can see the photosynthesis process or the water uptake process or biomass partitioning process or the yield simulation process. So, looking at the flow chart, that gives a better understanding of the interactions between the components in the model, and that gives a feedback loop and dependence, how the cause and effect relationship, what factors depends upon what variables depends upon what are the factors influencing variables, that is represented in this model with these symbols and with this flow chart. So, if you see, they can discuss these symbols, this rectangle, this that shows the represent the label. The label represent the state variable at a point in time and is shown by the rectangle. So, this in compartment models, the label represented by rectangle. So, this arrow is given, this small arrow I can show you how the label does represent as a rectangle. So, label represented by the state variable, this is this represent label. So, label means, say this is the state variables and this is the one is the rate variables. The rate variables. Label represent the state variable that indicate the state of the system at any point of time, and say this is the label and this is the rate. So, symbol label means state variables. In crop model you have the biomass, you have the leaf weight, you have the stem weight, even soil water content. So, those variables they change with time, they are not constant, they are not parameters, these are the state variables. State variables are represented by these known labels. So, this is the rate variables means the flow per unit time, rate variable, suppose you can say growth rate variables. So, rate variables are represented by these symbols. These are the symbols used to represent different variables in the crop model. So, label you can have the crop leaf area index also changes over time, crop biomass, that is a gram per meter square, that also changes over time. we can see the stem weight or the root weight or the leaf weight, that changes over time. Soil water content is not constant, that changes over time, depends upon the rainfall, depends upon the evaporations and the infiltrations, soil water content also changes. These are the state variables. State variables are represented by these labels, rate variables by this symbol. These are the symbols that represent the the model. So, which is explained here in detail. You can see these are the labels by rectangles, and the say it may be leaf area, it may be leaf weight, stem weight, biomass. So, soil water contents, these are the state variables that changes over time, even in the developmental stages, that also changes over time. So, crop is today as tillering stage, it may come to flowering stage, it may come to grain filling stage. So, that changes over time. So, those variables are state variables, they are also expressed in quantitatively. Okay, we will discuss that one. So, that changes over time. So, that is represented by this rectangle. So, this is the rate variables. So, I discussed also the rate variables. The rate symbol flow from one compartment to another, from a source to a compartment or from a compartment to a sink. So, what is source and what is sink? Source we can say the environment, source and sinks are represent environment of a systems. We can say temperature, we can say rainfall, we can say water come from different source. So, that represents source of the systems, that this is the symbol for the source, and this rate the flow from one compartment to another compartment, that is represented by the rate variables, the rate of flow, rate symbols flow from one compartment to another compartment in this model. And the source and sink, this is the symbol to represent the source of the model, source and the sink of the model. This is the source and the sink represented by this symbol. A source and sink represent the environment of the system. So, that flow occurs from a source in the environment into the system. So, without affecting the environment, source and sink. And this symbol you can see the D, this represent this as a, you can say auxiliary variables. So, what is auxiliary variables? So, that is these variables they may not be part of the systems, but these variables that influence the state variables, state of the systems, the process of the systems, this influenced by these auxiliary variables. Like you can say canopy cover, canopy cover that influence the state of the the biomass simulations or the biomass partitioning, that depends upon the canopy cover. Leaf area index sometimes we can take the auxiliary variables. These are represented by these symbols, auxiliary variables. These are the this may be inputs, this may be parameters that influence the rate and they influence the state variable of course definitely. So, these are this represented by this symbol, these are the auxiliary variables. Then you can see the E, that is a pathway for material flow. Pathway for material flow. So, why I am saying when you go to a flow chart of a model, so there how these are synchronized, we can say how they interact with each other, different components of the model, that can be represented using this flow chart. So, this is a pathway for material flow. This talks about the resources, you can say the water or the biomass or the carbon resources, how they are acquired resources and they are distributed and partitioned between the plant component, crop components, that is represented through the solid lines, that is a pathway for material flow. Like you can say biomass, in case of crop, the biomass is partitioned to leaf or the stem, it goes to root, it goes to the storage organ as well. So, the transformation, the partitioning of this biomass as a different parts of the plant crop, that comes from the pathway for the material flow, how the moves. That means, how the resources are the acquired and the resources are the transfer partitioned to different plant parts, that is represented by this solid line, that is a pathway for the material flow. And this the dashed line, dotted line you can say this one, this is the pathway for information flow. So, pathway for information flow, so that also influence the rate of the processes is influenced by this information. So, this indicates how the processes are influenced by, we can say the example like temperature, you can say the temperature pathway for information flow. The temperature that influence the rate of the processes, the rate of a process that is influenced by temperature or the radiations or the other parameters, they influence the process. So, this is a pathway for the information flow. So, these are the symbols, these symbols used in crop modeling. The symbols are brought from the Forester notation 1961, and the symbols are used to represent a flow chart. The flow chart means like we will discuss in the later classes how the flow chart represent the interaction among the components, the transfer, the movement flow from one compartment to another compartment, how the state variable, particularly state variables are influenced by the other parameters, and the rate of the state by rate of the flow from one compartment to another compartment, how they are influenced by different parameters or the constants or the another variables. So, those these processes in the model particularly, so they are represented using this Forester notation. So, these notations are very important somebody to understand this one, because when you go for the modeling and simulation writing a code also on the flow chart, you need to use these symbols to represent a model. So, these are the particularly for the main focus of the core part of this lecture is to familiarize you with the symbols, because these symbols will be used for the different variables, different parameters in the models. Like we have the, you need to represent the leaf weight, stem weight or the crop biomass. So, you have to use these rectangular symbols to represent this crop biomass or the leaf area also that changes over time. Leaf area index you can say, or the leaf weight, stem weight or the grain weight also that changes over time. That is. So, this is the rate variable flow of water, rate of flow of the water, rate of flow of the rate of changes in the biomass that is represented by this the rate variables. Source is the environment, source are sink. So, these are the auxiliary variables or the pathway for the material flow, this pathway for the information flow. So, these are the symbols you need to know for this Forester notations or the we can say symbols of the compartment models, the compartment model symbol that is used for representing the crop models. These are the just explaining. So, these are the applications of the compartment models in agriculture. So, we are applying particularly we are the crop growth we are doing for the photosynthetic partitioning into roots or the shoots or grains. So, that is used for this compartment models. Then you are the nutrient cycles, mineralization, leaching and uptake of nutrients, that is also represented. And the crop growth you can say this the biomass partitioning, so say crop growth and also soil water dynamics. Soil dynamics also that is represented by this how the water flow from one layer to another layer. So, there are different layers in the soils. So, flow from one layer comes to another layers and from another layers depends upon the rainfall, infiltration, evaporation. So, this how the changes that is also represented by this compartment model symbols. So, you can say the soil compartments you can see field capacity, wilting point, saturation, you know what is the field capacity being agricultural engineering or agricultural science students. So, you must have idea about the field capacity of the soil, wilting point of the soil, saturation. These are the you need to familiarize yourself, because these are the inputs that we used for the as a crop models, the soil water holding capacity. You should have the information on this. Then plant compartments we can say leaf weight or the stems or the roots weight, storage organs. So, these are the plant compartments. Allow simulation of feedback effects like such as nutrient limitation, reducing the biomass accumulation. So, these are the some of the processes which are represented by this compartment model symbol. So, from this we can see, so what is the summary and takeaway from this lecture, we can say crop models simulate the biological process, process mathematically predict the growth and yield. So, definitely that we have explained earlier. System approach helps in integrating the soil, crop and environmental factors. So, particularly this crop compartment modeling simplifies complex interaction into quantifiable flow and storage. So, using this compartment model symbols that gives a better visualizations and the better understanding of this users particularly the input output relationship, how there is a interaction among the inputs and how the variables are they are the quantified and how the quantification of the variables and how the rate of the processes that is influenced by the different parameters or the variables inputs. So, they are explained by this representations in these models. Then the Forester notation that provide the standardized visuals for the model structures. So, understanding these principles form the foundations of the state variable modeling and crop system simulation covered in that we will discuss in the different lectures, but particularly for this lecture the students all you should familiarize the symbols and the symbols used for the different symbols for different purposes. So, when you go for the writing a program or particularly for the making the flow charts, logic of flow charts. So, these symbols are essentially very important and to understand the process. Once you understand processes, then how the processes are linked, then you will be able to give these flow charts using these symbols and that indicates using flow chart indicates how the inputs do interact with each other. I hope this lecture will give you some understanding about the going forward for the next lecture, as when you go for the modeling scenario different processes, how these symbols can be utilized for the other lectures. So, with this I thank you all.